Welcome everyone. Can everyone hear me? Awesome. How is things on campus today? Will you guys be able to gain access to campus or are everything still in limbo? Gained access, could not leave. Okay, so I assume protest action are continuing. Okay, that's why I suggested for this class to be online as well. But let's start with today's lecture. This lecture is also going to be recorded. I'm going to re-upload yesterday's lecture and today's lecture to YouTube and provide you guys with a link to it. But for this lecture, we are going to look at what is the nature of astronomy, the nature of science, the laws of nature, numbers in astronomy, where are we in the universe, time scale of the universe, history of astronomy, and then finally end with important astronomy discoveries. Do you guys have any questions this far? Okay, so astronomy is defined as a study of the objects that lie beyond our planet Earth and the processes by which these objects interact with one another. So astronomy is not just about observing these objects, but also to understand what is the physics behind those objects, what processes are inside them, what processes do they have a secondary effects on the universe around them, and how everything fits in together. But also astronomy is also about a much bigger picture. It is also about humanity's attempt to organize what we've learned in the clear history of the universe from the instant of its birth in the Big Bang to where we are today and how everything fits together. So for this, we consider the history of the universe. We will see again and again that some cosmos evolve. It changes in profound ways over long periods of time. So for example, the universe made the carbon, the calcium, and the oxygen necessary to construct something as interesting and complicated as you. And today, many billions of years later, the universe has evolved into a more hospitable place for life. So did you guys know that calcium, carbon, gold, silver, platinum are elements that's not naturally occurring on Earth? And those elements were actually formed in supernova explosions. So when the Earth was formed, when stars went supernova, they caught all the elements that was fused during those processes, and that came and formed Earth. So most of our natural elements we see here are not naturally occurring processes on Earth, but rather was from a supernova remnant explosion. So therefore you can argue, due to the calcium in your bones, the iron in your blood, that we are literally made out of star stuff. Do you guys recognize this image? Yeah, and what is it? Yes, it's a timeline of the out of universe started. So right here at the left, we can see the Big Bang and where we are now 13.8 billion years later. And to understand the history of astronomy, we need to understand where we all came from. So if we zoom in on this, we have the Big Bang. And then 400,000 years after the Big Bang, we have the Dark Ages. The first light from the first stars emanated about 560 million years after the Big Bang. And here we are today, 13.8 billion years later. Do you guys have any questions? So what causes the universe to evolve? We will delve in one of our chapters. I think it's chapter 13 or 14. But everything keeps evolving around us. So some stars get born, and at the end of its life cycle, a certain star dies. Depending on its size, it causes secondary effects. So that can cause different stars being formed. So galaxies are constantly changing. And that causes the universe to evolve. The universe is also constantly expanding. So all of those features causes the universe to explore. And that is what we're going to learn throughout this module. What was present in the Dark Ages. So in the Dark Ages, we call that basically the primordial soup. So that is when the first atoms start to form. So when the universe began, basically the only atoms that existed after that was during the Dark Ages was hydrogen, because it's the first element on the periodic table. Then hydrogen fusion started happening, and we had helium. And then from there on, the first stars was born. So while the Big Bang created all the first helium atoms, that was the Dark Ages, and there was no light during the Dark Ages, but that is when the fundamental early building blocks of the universe began. And then when the first light has happened, that is the first stars where first hydrogen fusion starts to happen, and first light was being emitted. But we will learn about all these stages throughout the semester. So the ultimate judge in science is always what nature itself reveals, based on observations, experiments, models, and testing. Science is not merely a body of knowledge, but a method by which we attempt to understand nature and how it behaves. This method begins with many observations over a period of time. From the trends found through observations, scientists can model the particular phenomena we want to understand. Such models are always approximations of nature, subject to further testing. So one thing that's important, where we need to start out with, is how to model everything around us. So the first thing in science is we need to set up models. And the only way we can set up models is by observing what's happening around us. So if I ask you guys, what will a model of the night sky perhaps look like? What would you say? Yes, where constellations will be. So this is one of the earliest models where you look at the night sky and you see everything moving around you. So one of the earliest models of the universe was the Earth is the center of the universe, and everything revolves around Earth. Is this model correct? No. And only through observations of the natural world around us, we determined this was wrong. And in fact, the sun is the center of our solar system. And in our solar system, everything revolves around our own sun. As we continue adding knowledge to our model, we realize that the sun is not the center of our universe. And in fact, we will learn about this in later chapters, but our universe doesn't have a center as well. And that's a common misconception. So people wrongfully assume that a Big Bang started at a central point and we can trace to where that point is. That is not correct. The Big Bang happened everywhere at once, simultaneously. So therefore, the Big Bang doesn't have a central point, but happened everywhere at once. So what is the nature of science? So when they are first proposed, new models or ideas are sometimes called hypotheses. You may think there can be no new hypothesis in science such as astronomy, that everything important has already been learned, but nothing could be further from the truth. So two of these hypotheses we are still working on is what is dark matter, and also what is the origin of life. Can you guys think of more examples? Yes, aliens. Do aliens exist? Do they not? Are there life anywhere else in the galaxy? What else? Yes, the first few seconds after the Big Bang. So we can now, with simulations, get very close to that point. What happens outside of our universe? Yes. Theory of wormholes, the multiverse theory. Yes, all of that is correct, and that is still hypotheses and concepts we are investigating. So resolving these issues will require difficult observations done at the forefront of our technology. And all such hypotheses need further testing before we can incorporate them fully into our standard astronomical models. So one of the most important models ever constructed is the standard model of the universe. And everything we know about science and biology fits into this standard model. And we continue to add new information to this model. And what is important is the last point of this statement. Our hypothesis must be a proposed explanation that can be tested. The most straightforward approach to such testing in science is to perform an experiment. If the experiment is conducted properly, its results either will be agree with the predictions of the hypothesis, or they will contradict it. If the experimental result is truly inconsistent with the hypothesis, the scientist must discard the hypothesis and try to develop an alternative hypothesis. If the experimental result agrees with the predictions, this does not necessarily prove that the hypothesis is absolutely correct. Perhaps later experiments will contradict the crucial parts of the hypothesis. But the more experiments that agree with the hypothesis, the more likely we are to accept the hypothesis as a useful description of nature. So one thing is, have you guys ever seen a black sheep before? But black sheep do exist. So if I state a hypothesis that all sheep are white, how do we test it? So if we want to test our hypothesis that all sheep are white, we just go to a lot of sheep farms and see if we can see a black sheep. And yes, black sheep are a genetic mutation that is not very common, but yes, every now and again you can find a black sheep. So that means our hypotheses are wrong, and we did experiment. We went to farms to see if we can find it. So now we can adjust our model and our hypothesis that black sheep do exist. So if I state with our hypothesis and our model, do red sheep exist? What do you say? Not possible. And how do we know it's not possible? Yes, it cannot be observed. So one thing that is important with this, and where this theme is leading up to, we need to set up models of the universe and models that we are designing. And so the first thing in our model is our understanding of what's being tested, of what needs to be observed, is modeled. So usually with mathematics. So from this point on forward, I don't want you guys to think about mathematics as just mathematics. I want you guys to think about it as a language. And how do you guys learn a new language? Any suggestions? Yes, you practice it. And math is the language that the universe speaks. So to understand the language of math, you need to practice it. So the more you practice it, the better you become at it. And then from your mathematical models, we can set up simulations. And from our simulations, we can go to observations or experiments. And if our observations or experiments doesn't correlate or fit into our simulation, means our mathematical model is wrong and our hypothesis is wrong, and therefore you can adjust it. So astronomy is also sometimes referred to as observational science, because everything in the universe we try to observe. And also much of astronomy is also a historical science. So astronomy is also considered as one of the oldest science fields because it's literally hundreds of years, even a couple of thousand years old. And also it is historical science because we base our observations on historical observations. So in the cosmos, things don't really change in a couple of hours or a couple of days. Some observations takes years before you take or observe something to change. So therefore, you compare your data you are collecting now to data that has been collected years ago, and therefore it forms part of the historical science. So here, for example, we can see where we are. So the Milky Way galaxy. The closest other galaxy to us is Andromeda, which is this red galaxy over here. Here in the yellow is large galaxies visible, and the blue are small galaxies. So if you take our own galaxy, for example, it's about 75,000 light years across. Do you guys know what a light year is? Yes. So can someone perhaps explain it? Yes, it's a measure of distance. So someone's saying, yeah, it's time for light to travel a distance. Yes, so light year is the distance light travels in 1 year. So if I say a star on the other side of our galaxy is 75,000 light years away, that means that light from that star takes 75,000 years to reach us. So if something happens to that star, if there's a change in that star, we can only see that change happening after 75,000 years. So that is why astronomy is also a historical science. So over centuries, scientists have extracted various scientific laws from countless observations, hypotheses, and experiments. These scientific laws are, in a sense, the rules of the game that nature plays. One remarkable discovery about nature is that the same laws apply everywhere in the universe. The rules that determine the motion of stars so far away that your eyes cannot see them are the same laws that determine the arc of a baseball after a batter has headed out the park. Note that without the existence of such universal laws, we could not make much headway in astronomy. This is not to say that our current scientific models and laws cannot change. New experiments and observations can lead to new, more sophisticated models. Models that can include new phenomena and laws about their behavior. The general theory of relativity proposed by Albert Einstein is a perfect example of such a transformation that took place about a century ago. It led us to predict and eventually to observe a strange new class of objects that astronomers call black holes. Only the patient process of observing nature ever more carefully and precisely can demonstrate the validity of such new scientific models. So if we look at these scientific models, we can classify a black hole of a region of space that is so intense that no matter or radiation can escape it. But something we still don't understand is what's happening inside a black hole. So we understand the theory up to a black hole. So something we will learn about in this module is there's a region, or you can call it an invisible or imaginary boundary line around a black hole called the event horizon. So if you are outside of the event horizon, you can still escape the gravitational pull of a black hole. But if you cross over the boundary, over the event horizon, then you cannot escape the gravitational pull of the black hole anymore. So our understanding of physics, we know exactly what happens all the way up to the event horizon, but we have no idea what's happening inside the event horizon because we cannot see it, because no light can escape the pull, so we can't see visible light, we can't take measurements, and that is where our understanding of the laws of nature governing black holes breaks down. But if we look at our normal laws of physics, gravity is the same everywhere in the universe. It states the bigger an object is, the more mass it has, the bigger the gravitational pull is. That is laws of physics and laws of nature, and that laws of nature is the same everywhere in the universe, doesn't matter where we are. So when we start looking at the laws of nature, in 1915, Albert Einstein developed the theory of general relativity, where the theory shows that gravity influences the motion of light. Do you guys know what, so Albert Einstein won the Nobel Prize in Physics. Do you guys know for what topic or what discovery he won the Nobel Prize for? Any ideas? So people has the common misconception that he won the Nobel Prize for Physics for the relativity, but was not. He won the Nobel Prize for Physics for the photoelectric effect that you probably heard or learned about in your high school careers. So yes, you are correct, it's the photoelectric effect. But he is more famous for his theory of general relativity and later on special relativity. So the next part of slides, you don't need to memorize or learn anything for the semester test, but it's just to show you how everything fits together. Question, sir, how do we know gravity is universal in even a black hole if we have never been able to enter a black hole and observe it? So how we know gravity is universal is we can observe gravity everywhere in the universe. So we can observe gravity on Mars. We have put all humanity has landed rovers on Mars, and to land a rover of Mars, you need to know what a gravitational pull of Mars is. We landed people on the moon, so we know what a gravitational pull of the moon is. So the gravitational pull of the sun is what's keeping all our planets orbiting the sun. the gravitational pull of the supermassive black hole at the center of our Milky Way galaxy is for keeping all the stars in our galaxy orbiting the central point, the black hole. So we know what gravity is. So that's a universal law. The only thing is we don't know what governs the laws of physics inside a black hole, but everywhere else in the universe, we know gravity is constant and how it operates. I hope that answers your question. So in 1915, Einstein, so you mentioned that radiation can't leave a black hole, but what about gamma ray bursts? So gamma ray bursts are not from black holes. Gamma ray bursts are usually in stars that go supernova. That's something we will talk about later in this module as well. So this is just background information. You don't need to know this formula. You don't need to know how it works or need to mention somewhere. This is just pure background information about astronomy. So in 1915, Albert Einstein came up with the theory of general relativity. And this is the field equation of relativity. So he has this equation that explains relativity, but there were no solution for this equation. And we are building on top of that. So that's also something we will talk about later in this chapter, of who solved the field equations and how it's now a fundamental part of our understanding of the universe and a fundamental law of nature. So if you think about language limitations, we have language limitations in describing the universe around us, and the only language that is fitting to explain the universe around us is math. And like I said, I don't want you guys to think about math as math, but rather as the language the universe speaks. So one thing that stands out in this slide is Arabic. Do you guys wonder where Arabic numerals comes from, or what Arabic numerals is? Yes, Arabic numerals is the number system we are using every day. And it's called Arabic numerals because it's originated in the Middle East. So that's a bit off-topic point, but in the early second part of the 2nd century, so from the year 1100, 1200, the most scientific work and mathematical work that happened in the Middle East. That was the center of science and knowledge. But then the Dark Ages happened and religion took over, and then scientific and math knowledge was banned in the Middle East, and they still haven't recovered from that ever since. But that is a topic for a bit off-topic discussion, just something interesting. So when we look at this, this is the language the universe speaks. So for your future careers, get comfortable with math. See it as a language, and that will help you in your future studies. And to understand this language, we need to understand numbers. And numbers are important in astronomy. So in astronomy, we deal with distances on a scale you may have never thought about before, with numbers larger than any you may be encountered. So we adapt 2 approaches that make dealing with astronomical numbers a little bit easier. So when we look at numbers, we have scientific notations. So a millionth is 1 times 10 to the power minus 6. And if we go to the other side, around 1 million is 1 times 10 to the power 6. So I'm sure you are all comfortable with decimal form and scientific notation. Awesome. So one unit we generally use in astronomy is the astronomical unit. So The astronomical unit is the distance from Earth to the Sun. So the orbit of Earth to the Sun differs a bit every year. So on its closest point, it's about 200,000 kilometers closer, along furthest point, 200,000 kilometers farther around the Sun. But we use the average. So on average, the Earth from the Sun is 150 million kilometers away. So we define one astronomical unit as 150 million kilometers. So if you think about the star Neptune, so Neptune is about 9 astronomical units away from Earth. So which is more difficult to work with? If you say 150 million times 9, or just saying 9 astronomical units? It's more difficult working in kilometers, because if you work in space, the distances are so vast that you work with very big numbers. So it doesn't help saying something is so many million kilometers away. It's easier to say it's 1 astronomical unit away, 2 astronomical units away. Does that make sense? Awesome. So will we need to memorize what 1 AU is equal for a test? Yes. So that's something for a test and exam you need to know is what, so I can ask you, what is an astronomical unit? So to think about it going a little bit further, so if we go even to further distances, then astronomical units becomes quite a little bit too small. So we know 1 light year is the distance that light travels in 1 year. So that is roughly 300,000 kilometers per second. So if you think about it, 1 light year is 36,000 astronomical units. So again, then the distance astronomical unit becomes a little bit too small. So then we need bigger units, then we go over to light years. So if you put it at distance, the distance from the Earth to the Moon is 1.3 light seconds. So that means it takes light 1.3 seconds from the Moon to reach Earth, or the Earth to reach Moon. Sun, the speed of light traveling from the Sun towards Earth is 8 light minutes. The Sun to Neptune is 4 light hours. The Sun to Proxima Centauri, the nearest star to us, is 4.2 light years. The Sun to the star Polaris is 433 light years. The Sun to the center of our Milky Way galaxy is 100,000 light years. And the Milky Way galaxy to our nearest other galaxy, Andromeda, is 2.5 million light years. So there you can see how things dramatically scales upwards. So at some point we will realize also that astronomical units, that light years actually becomes too small. So the next unit we are using is called a parsec. And 1 parsec equals 3.6 light years. So I'm not going to ask you how to determine a parsec, but I just want you to know for test and exam that 1 parsec equals 3.26 light years. And to determine what 1 parsec is, let's see we are in a spaceship and we travel far away from the Sun. And we are so far away, and if you look at the orbit of Earth around the Sun, we can see here the distance from Earth to the Sun is 1 astronomical unit. And if we're so far away that this angle right here is 1 arc second, then that is a parsec. So a parsec is the angle subtended by 1 astronomical unit is 1 arc second. So the distance is defined as 1 parsec. So astronomers can measure angles very accurately. So full circle is 360 degrees. So 1 degree divided by 60 parts gives arc minutes. And 1 divided into 60, and 1 of these parts divided by another 60 gives arc seconds. So 1 parsec equals 3.26 light years. Are you guys happy with this definition? Are you guys happy with the explanation that 1 Light, 1 parsec is 3.26 light years. Okay, cool. So who of you are Star Wars fans? So in Star Wars Episode 4, you'll say, oh yeah, there's a bit of a science error they made there. They say that Han Solo with the Millennium Falcon did the Kessel Run in 12 parsecs. That is wrong. A parsec is not a measure of time, it's a measure of distance. So that's just one small mistake they made in the Star Wars universe. So if we start out and I ask you guys, where are we in a universe? What would you say? Yes, on Earth, but we can start with a smaller scale. So if we were on campus right now and had no protests, we would say we are at the University of Pretoria and we are in the IT building. So if we look at where we are, here is the Humanities building, here is where the Student Centrum is. So the next building on here is the IT building, is this building right here. And we would be in IT 44, so we would be in a lecture room in this building around here. So if I say, well, can we zoom out a little bit further to see where we are? Can we zoom out a little bit more? Yes, we can. So if we zoom out a little bit more and look at Google Maps, we'll see here, here's our pin. We are at the University of Pretoria and we are in Pretoria in Gauteng. Do you guys think we can zoom out even more? Yes, so if we zoom out more, we will realize we are in South Africa. And here we are at University of Pretoria. So can we zoom out even further? Yes, so if we zoom out further, we can look at the Earth from a great altitude. Can we zoom out even more? Yes, we can. We can see Earth as a whole. Do we think we can zoom out even more? Yes. So the next step will be we can see the moon. So the moon is roughly at average 380,000 kilometers away from Earth. If I ask you, can we zoom out more? Yes, so if we zoom out more, we can start seeing the sun and our own solar system. Can we zoom out even more? Yes, we can. So if we zoom out more, we can see where we are right now. So here we can see the sun, we can see Earth, Mars, Jupiter, Saturn, Neptune. Here we can see the Great Hydrogen Wall, the interstellar medium, the Oort cloud. We'll learn about everything. Here we can see Alpha Centauri, the closest other star to us. Do you think we can zoom out even more? Yes, we can. So here we can see the Milky Way galaxy. So something interesting, this right here is a smaller galaxy orbiting our own galaxy, and here as well, they're called the Magellantic Clouds. So we have the large Magellantic Clouds and the small Magellantic Clouds. We'll learn about them a little bit in later chapters, but our Milky Way galaxy is actually putting them into us and forming part of the Milky Way galaxy. And here we can see at one of the outer arms and outer edges where we are located in our own galaxy. Do you guys think we can zoom out even more? Yes, we can. So if we can zoom out even more, we can see different galaxies. And different galaxies are also categorized together. So our own Milky Way galaxy forms part of the local galactic group. So galaxies clump together as well. And that brings us to where are we in the universe? So I see one period has passed now. Do you guys want to take a short 5-minute break? Okay, so I see yes and no or sure. So let me have a quick poll. Okay, so I've just created a poll that you guys can vote for small break or not. Okay, there's 12, 14. Okay, there's 10 more people that needs to vote. Okay, so it seems like people are switching back and forth, so it's 50-50. So, okay, let's continue on then. So it seems like the majority of the class don't want a small break. Let me just get to the slides where I need to be. So do you guys recognize this image? This is probably one of the most famous images in astronomy history. So when the Hubble Space Telescope was launched in the 1980s, you guys are all familiar with the Hubble Space Telescope? So I see here a no. So Hubble Space Telescope is a telescope that's in space orbiting around Earth. The telescope is around about the size of a school bus, but it is one of the first telescopes that was put in orbit. And the reason that is to not be influenced by light pollution. And it's also one of the most sensitive scientific equipment we have. So the Hubble Space Telescope has recently been replaced by the James Webb Space Telescope, but Hubble is still operating and being used. So just beside the moon, they chose a small area that is in space that is 1 centimeter by 1 centimeter in size. And they pointed Hubble towards that area and they took a long exposure picture. And this is the picture that came out. And every little dot, every light you see in this image is a galaxy. And that is known as the Hubble Deep Field image. If you Google the Hubble Deep Field image, this is the image that will pop up. So every little point, every star, every object you see in this image is a galaxy. And that shows just how many galaxies. Sorry about that. It seems my internet just connected. Can everybody still hear me? Awesome. So that's why I'm asking, where are we in the universe? Where are we in the universe? And to put it in perspective is, where did our universe start? So our universe started with the Big Bang to where it is now. And to put that cosmic time frame into perspective of how everything developed to where we are now, we can put everything in 1 year. So let's say when the Big Bang started, put it on a time scale to where we are now today. Let's put that in 1 calendar year. So the Big Bang would have occurred in January. In March, the first light in the universe would start to begin. In May, the Milky Way galaxy was formed. In August, planets in our own solar system formed around about August, September. So in September, our solar system forms and life on Earth begins. In October, Earth's atmosphere becomes oxygenated. And then November, as first complex life forms appear on Earth. And now when we get to December, and December is where everything starts happening very fast. So the 19th of December is vertebrates appear. The 20th of December, land plants appear. 25th December, dinosaurs appear. 26th December, mammals appear. 30th December, dinosaurs becomes extinct, and the 31st of December is where we are right now. So putting it in a perspective as to where we are right now. So if we look at some of the most important historical discoveries and when they lived, is astronomy started with the Chinese in 2000 BC. Then the Babylonians and the Greeks at 1000 BC. We have Ptolemy that we learn about at the year 0. And then in the year 1500, we have Tycho Brahe, Copernicus, Hans Lippershey, Galileo Galilei, Johannes Kepler, Isaac Newton, William Herschel, John Gale, Albert Einstein, Edwin Hubble, Carl Jansky, Grote Reber, the Hubble Space Telescope, the Chandra X-ray Observatory. So if we put it on a time scale and we see what is the most important aspects of what these people discovered is the Chinese started charting and recording eclipses. The Babylonians make accurate predictions of planets in their visibility. The Greeks develop important ideas about Earth, stars, and planets. Ptolemy wrote about Greek ideas and that the sun circled around the Earth. Tycho Brahe analyzed motions of planets and predicted the motions most accurately. Copernicus proposed the sun as the center of the solar system. Hans Lippershey invented a telescope by placing simple lenses at the end of a tube. Galileo Galilei improved the telescope by making a reflecting telescope. Johannes Kepler proposed planets orbit the sun in elliptical orbits. Isaac Newton invented reflecting telescope and also the laws of these universal laws and also calculus. William Herschel discovered the planet Uranus. John Gale discovered the planet Neptune. Einstein was relativity. Edwin Hubble is the expanding universe. Clyde Tombaugh discovered Pluto. Carl Jansky is radio astronomy that we'll talk about as well. Grote Reber has made the first radio telescope. The Hubble Space Telescope was launched. The Chandra X-ray Observatory, so that's also a space telescope, but it's only designed to observe X-rays. So where does everything fit in? So where do we start with our observations? So the first thing that is important is pattern recognition. So humans have been looking up at the sky and making observations since the earliest ancient civilizations, and likely before that too. So the simple power of pattern recognition is considered the separation between sentient and non-sentient beings. So did you guys ever realize that humans are fascinated with things to be perfect? One idea is symmetry. And did you guys know in nature, nothing is naturally symmetric? Did you guys realize that? So nothing in it. So, and also we like things to be linear. It just makes the math easier if things is linear. But you also know in that natural occurring world around us, nothing is linear. Everything is in a form of exponential. So the most likely pattern we'll see around us is exponential. But exponential is very difficult to analyze. So therefore, we like to put everything on the linear scale. So you guys have done logarithms at school. And logarithms are used to put everything in a linear scale, and we can analyze it earlier. But nothing is symmetrical. So that's why your face is not symmetrical, because that's something that's not naturally occurring. But us as humans like things to be aesthetically pleasing. And that's why everything we want to use is symmetrical and linear. So that is why linearity is important, because it makes things easier to analyze. And our minds are set up to do pattern recognition. So if you look at a night sky, the constellations we can see, that's patterns. If I ask you guys to analyze something, the easiest way you will probably start out with is looking for patterns. And that is why it is important for us. And that is why astronomy started, by looking at pattern recognition of the universe around us. So in 1543 AD, when Copernicus became the first person to demonstrate the math behind such an insane idea, he was universally ridiculed. The fact that the heliocentric model was so revolutionary that Copernicus was actually afraid to publicize it. However, once the idea was finally accepted, it eliminated many problems with older astronomical studies, and is considered the first major realization of our place in the universe. We realized that the sun is a star, not a god, and that we aren't located at the center of the universe. So with the earliest patterns we saw was that everything revolves around Earth. But Copernicus made observations and discovered that that's not actually true. Everything in our observable space, in our solar system, actually revolves around the sun. So another way you can look about it is to think about it as old charts. So that's why a lot of Greek and Roman mythology is centered around the sun and see the sun as a god. But Copernicus changed that with his revolutionary theory. Another important discovery are Kepler's laws. So keep in mind, in a test and exam, a hint I can give you guys is I can ask you what are some of the most important astronomy discoveries. So we can start out by pattern recognition. We can say it is Earth moves around the sun. And also Kepler's laws. So who of you are familiar with Kepler's laws? So we will learn about Kepler's laws in details later on in this module, but Johannes Kepler proved that planets move around the sun in elliptical orbits rather than perfect circles. In 1609, this was revolutionary because it meant that the distance between the planets and the sun changed over time. Finally, the world understood the reason behind seasons and the apparent motion of planets. Without these discoveries, astronomers would have had a much more difficult time trying to explain what the sun's influence on Earth changes and why the speeds of other planets seem to vary over time. And Kepler described it with his three laws that we will discuss in a later chapter. So I've only heard of it, but I don't fully understand how he got to the conclusion. Yes, we will learn about that in a later chapter, and it's actually quite fascinating. Another thing that's quite important is Jupiter's moons. So Galileo discovered 4 moons of Jupiter in 1610 using a telescope that he designed and created himself. They were the first moons discovered that didn't orbit Earth, making them the most important piece of evidence for Copernicus' model of heliocentrism. This was tangible proof that planets other than Earth had moons and that we weren't as unique as we thought. So During that time, they thought that everything revolved around Earth. But with the discovery that other moons are actually orbiting around a planet, planted the seed that Copernicus is right, that everything is not revolving around Earth, because now there's evidence that there's other moons orbiting around another planet, and that the model of heliocentrism is actually correct. So Jupiter's moons is a good discovery and something important to remember, and also something to distinguish. Galileo wasn't the first person to discover a telescope. He was only the first person who started using a telescope for astronomy purposes, but not the other way around. A lot of people usually make these honest tests and exams, state an important discovery as Galileo created the telescope. That's incorrect. Galileo used the telescope to discover other moons orbiting a different planet. Does everybody understand that? Awesome. Another important astronomy discovery we're going to talk about in the next lecture is Herschel's map. So astronomer William Herschel and his sister Caroline systematically mapped the night sky, listing thousands of stars and nebulae in almost a 5-decade process. Published in 1834, his map revealed the shape and size of the Milky Way, which turned out to be disc-shaped rather than a sphere. And he also discovered Uranus. So he determined that the stars in the Milky Way is situated in a disk around the center part that's now what we now know as a supermassive black hole, but not like in a balloon or a sphere around everything. Then also important discovery is the theory of relativity. Before Einstein knocked it out of the park with his theory of relativity, the world of astronomy strictly obeyed Newton's 3 laws of motion. Everything changed when Einstein argued that motion was relative and that light could be affected by gravity. The possibility that mass could warp space-time and at large enough mass could even bend light shook the scientific community, because light was considered an absolute constant. The theory revolutionized astronomy and solved many problems that had been deemed impossible with Newton's conflicting laws. Another important discovery is the expanding universe. So when Edwin Hubble told the world that the universe is expanding, it was groundbreaking to say the least. After tracking the movement of other galaxies, which he was also the first to discover, he concluded that they are moving away from us, while also constantly accelerating. He also concluded that most of the nebulae visible in the night sky were actually galaxies. This provides further evidence to support the theory of the Big Bang and changed our conception of the universe. Another important discovery is the cosmic microwave background radiation, or the CMB. Uniformly defined radiation that fills the universe was discovered quite accidentally by 2 Bell telephone employees in 1964 while working on satellite communications. Since light from an object 1 light year away takes 1 year to reach Earth, the CMB functions like a snapshot of the universe. The implications of this discovery were profound, since the uniformity of the radiation appears to confirm the nation of the universe originated in a single event from which everything else flows. The fact supports the theory of an expanding universe and therefore the Big Bang. So we'll talk about these 2 Bell laboratory engineers and also cosmic microwave background in a later chapter. But basically, what it means is the cosmic microwave background radiation is the fingerprint left behind by the Big Bang. So if you are still using older analog TV and you have that snowflake effect between the TV channels, and also if you have an analog radio, especially analog car radio, and you are looking for a station and you hear that sound in between stations, that's static, that is the cosmic microwave background radiation that we can still pick up that was left behind by the Big Bang, and that's situated at roughly 21 megahertz. But yes, we can still pick that up, and that is remnants of the Big Bang and evidence that the Big Bang actually existed. Another important discovery are extrasolar planets, meaning planets outside of our own solar system orbiting other stars. So an extrasolar planet, also known as an exoplanet, is a planet found outside our own solar system. The existence of exoplanets was not all that surprising, but a method by which they were discovered has changed the course of astronomy. So nearly 3,000 exoplanets have been discovered since 1988. Roughly 1 in 5 Sun-like stars have an Earth-sized planet within habitable distance from the star. So I like to call that a Goldilocks zone around that star. So if you know the size of the star, you can calculate what its energy output is, and then you can calculate an area around that star that is not too cold, not too warm, and just right to sustain life. So I like to refer them as Goldilocks zones. So if we use the statistics, assuming there are 200 billion stars in the Milky Way, that would mean 11 billion habitable Earth-like planets are in the Milky Way galaxy alone. And that is quite mind-boggling. Is everyone still following? Awesome. So another important thing that happened in astronomy is the first image of a black hole. Do you guys remember when this image made rounds on social media? Awesome. And then this is a bit food for thought. So the molecules that comprise our body are traceable to the cubicles of the centers of stars. These atoms and molecules are in us because, in fact, the universe is in us, and we are not only figuratively, but literally stardust. And that's like I said, we started out, all the molecules and building blocks in our DNA started out as remnants of supernovae. Are you guys happy with that explanation? Awesome. So that brings us to the final slide of part 1 of the lecture. So let's take a small 3-minute break until we're waiting for the next lecture slides to upload. Then we will continue. Yes, so Almari, I've seen your email. Apologies about that. Last 2 days was hectic. After class, I will reply to your email. It's a pleasure. So I think those slides have uploaded. So let's start with our second set of lecture slides. So the first set of lecture slides is chapter 1, second set is lecture 2. So lecture 2 will comprise chapter 2 and 3 of the textbook. So for this lecture, we're going to look at why do we study astronomy? What is the scientific method? A user's guide to the sky and its motions, cycles of the sun and moon, cycles of the sun, motions of planets, astronomical influences on Earth's climate, the changeable moon, the motion of the moon, the cycle of the moon phases, lunar eclipses, and solar eclipses. So, let me start this lecture by one of the quotes of Neil deGrasse Tyson is the good thing about science is that it's true whether or not you believe in it. So if I ask you, why do we study astronomy? Any ideas? Why do we do astronomy? Why am I an astronomer? Why do we study astronomy? Why do people study astronomy? To explore space, yes. To better understand how the universe works, yes. To discover more about the universe. All those answers are correct, but there's even a simpler answer. Is we as humans are a curious species. We want to know how everything works around us. We want to know how everything fits in together. And that is why we study astronomy. Then, besides knowing or trying to understand how it works, we have secondary effects. So the technology and science being developed usually finds its way to the general public. So one thing is, you know where cell phones comes from? Cell phones was invented primarily to the space race, to see what is the best form to communicate with spacecraft and people in space. So cell phones are one of the byproducts. GPS is one of the byproducts of astronomy, and we can continue on with the list as well. So the exploration of the universe will help us understand two fundamental questions. The first is, what are we? And the second question is, how do we know? So the question, what are we, is the first organizing theme of this course. Astronomy is important to you because it will tell you what you are. Notice the question is not who are we. If you want to know who we are, you may want to talk to a psychologist, sociologist, theologian, paleontologist, artist, or poet. What we are is a fundamentally different question. As you study astronomy, you will learn how you fit into the history of the universe. You will learn that atoms in your body had their first birthday in the Big Bang when the universe began. Those atoms have been cooked and remade inside generations of stars. And now, after billions of years, they are inside you. Where will they be in another 10 billion years? This is a story everyone should know. And astronomy is the only course on campus that can tell you that story. The question, how do we know, is the second organizing theme of this course. It is a question you should ask yourself whenever you encounter statements made by so-called experts in any field. Should you swallow a diet supplement recommended by a TV star? Should you vote for a candidate who warns of climate crisis? To understand the world around you and to make wise decisions for yourself, for your family, and for your nation, you need to understand how science works. So how do scientists learn about nature? And That is why I had in the previous lecture slides, we learn about nature by observing what's happening around us, creating hypotheses, and setting up mathematical models. So you have probably heard several times during your education about the scientific method as the process by which scientists form hypotheses and test them against evidence gathered by experiments and observations. Scientists try to form hypotheses that explain how nature works. If a hypothesis is contradicted by evidence from experiments or observations, it must be revised or discarded. If a hypothesis is confirmed, it still must be tested further. In that very general way, the scientific method is a way of testing and refining ideas to better describe how nature works. So the first thing we are going to look at is constellations. Are you guys familiar with constellations? So constellations are the images we can draw in the night skies. One of the most famous ones, probably in the southern hemisphere, is Orion and Scorpio. So all around the world, ancient cultures celebrated heroes, gods, and mythical beasts by giving their names to groups of stars called constellations. The constellations simply celebrate the most important mythical figures in each culture. The oldest constellations named in Western cultures originated in Assyria over 3,000 years ago, and others were added later by Babylonian and Greek astronomers. Of these ancient constellations, 48 are still in use. Originally, constellations were only loosely defined groupings of stars. Many of the faintest stars were not included in any constellation, and the stars of the southern sky not visible to the ancient astronomers of northern latitudes were not grouped into constellations. Constellation boundaries, when they were defined at all, were only approximate, so a star like Aldebaran could be thought of as part of Pegasus or part of Andromeda. To correct these gaps in the ambiguities, astronomers have added 14 modern constellations, and in 1928 the International Astronomical Unit established 88 official constellations with clearly defined boundaries. In addition to the 88 official constellations, the sky contains a number of less formally defined groupings called asterisms. The Big Dipper, for example, is a well-known asterism that is part of the constellation Ursa Major in the Great Bear. So here we can see the constellation Orion, and here we can see the constellation Scorpio that you can make. So we will learn about constellations a little bit further, but this is just an introduction to give us different attributes what we are working with. So the first thing is the constellations. The second thing is the star names. In addition to naming groups of stars, ancient astronomers gave names to the brightest individual stars. Modern astronomers still use many of those ancient names. Although the constellation's name came from Greek translated into Latin, the language of science until the 19th century, most names comes from the ancient Arabic, much altered by the passing centuries. So if you look at 90% of all stars has an Arabic name. Like I said, the Middle East was at some point the forefront of science and mathematics, and that changed. But that's why 90% of star names has Arabic names. Did you guys realize that? So that is just something to think about. So naming individual stars is not very helpful because you can see thousands of them. So how many names could you remember? Also, a simple name gives you no clues to the location of the star in the sky or to its brightness. A more useful way to identify stars is to assign letters to bright stars in a Greek constellation in approximate orders of brightness. Astronomers use Greek alphabets for this purpose. Thus, the brightest star in a constellation is usually designed alpha, the second brightest beta, and so on. Often the name of the Greek letter is spelled out as an alpha, but sometimes the actual Greek letter is used, especially in different charts. To identify a star by Greek's letter designation, you would give the Greek letter followed by the possessive form of the constellation name. For example, the brightest star in the constellation Canis Major is Alpha Canis Major, which can also be written as A Canis Major. So that is the Greek letter for alpha. So Alpha Canis Major. So the both identifies the star and a constellation and gives a clue to the relative brightness of the star. So compare this with the ancient name for the star, and that is Sirius, which does not give you any information about its properties. So something interesting, Sirius is the brightest star we can see in the night skies. Now currently around about 8 o'clock in the evening, when you look directly upwards to the 12 o'clock position, the brightest star you will see is Sirius. Something interesting, this image right here, do you know what constellation this is? Any ideas? This is Pleiades. So in the South African context, it's also known as the Seven Sisters, or in Afrikaans, the Sewe Sisters. But it's actually, its correct name is Pleiades. And you also know which logo Pleiades is. So the car brand Subaru uses Pleiades as its logo. So that's just something cool and interesting on the side. Yes, so the Seven Sisters is its informal name, but its scientific name is Pleiades. So also around about 8 o'clock in the evening, if you look upwards, you'll see the constellation Orion. So when it starts rising, it is upside down. So this star, brightest star Sirius, it's one shoulder, its other shoulder. The Three Sisters, you probably know, I've heard about. That's the belt of Orion the warrior. Here is his sword hanging from his belt. Here's his other leg. Here's his other leg. So my favorite object to look at is the center star of the belt. That is a stellar nebula where stars are formed and born. But we'll talk about that later on. But if we look in this constellation, we have Alpha Uranus, which is also known as Betelgeuse. So this is the star right here. And here we have Beta Uranus, also known as Rigel. And so on and so forth. We can go through the different stars of the constellation. Everybody still following? Awesome. So with this, we can go on. So we can say Sirius, the brightest star, forms part of Canis Majoris. So it's Alpha Canis Majoris, and it is the brightest star in the sky. So Betelgeuse is Alpha Orionis, and it's the brightest star in Orion, and so on and so forth. We can continue on with this naming scheme. So let me just check where we are right now. So the next thing is we need to determine a star's brightness. So astronomy usually describes the brightness of a star using the magnitude scale. And that's a system that first appeared in the writing of Claudius Ptolemus, also known as Ptolemy, in the year 140. So the system is probably originated even earlier. And most astronomers attribute it to the Greek astronomer Hipparchus. Hipparchus compiled the first known star catalogue and may have used the magnitude system in that catalogue. Almost 300 years later, Ptolemy used the magnitude system in his own catalogue, and successive generations of astronomers have continued to use the system. So it is categorized in a logarithmic scale. So when more fainter objects were detected, the scale was adjusted. So usually what I tip for, they ask for the test and exams. The naked eye can only see to magnitude 6. After magnitude 6, you need a telescope because it's too faint. So Polaris is around -2 of 2, bright magnitude 2. Sirius is around about -2. Venus is -5. The full moon is around about -13, and the sun's brightness is around about -27. Happy with these explanations? So this, the larger the magnitude number, the fainter the star. So this makes sense if you think of a bright star as first-class star and the faintest visible stars as sixth-class star. So ancient astronomers could only estimate magnitudes, but modern astronomers can measure the brightness of stars to high precision. So they have carefully redefined the magnitude scale. So here we can see the naked eye is magnitude 6, and the Hubble Space Telescope is magnitude 27. Do you guys have any questions so far? Okay, but I think we will call it for a day and end the lecture right here. I will be active for another minute or two. Otherwise, you guys are more than welcome to log off. I will see you in class next week, Monday on campus, unless the protest action lasts that long, then I will communicate with you guys beforehand. But hopefully I will see you guys next week, Monday. So have a wonderful evening and good luck with the rest of your week. So what is the magnitude of Webb? I'm not exactly sure what the magnitude of this James Webb Telescope is, but I will find out and report back next week.